Here's the bottom line. A net force causes acceleration, not velocity. And a net force is the vector sum of all the true forces. Look at this diagram here. As I stand here, not moving, what's my acceleration? 0. That acceleration is caused by this free body diagram. What that means is that this free body diagram has got to scream 0. That means that if my weight force is 200 something, that this force has to be just as big. Okay? Because my diagram has to scream 0 for my acceleration to be 0. Let's take a more complicated example. What if I were to lift up that slate and make it into a ramp? And I put that dry ice back on and it speeds up as it goes down the ramp. Now if I draw a free body diagram for that block of dry ice, the first force I put on any diagram is the weight force. This is the earth on the block. I then ask, are there any magnets? No, not yet. So what touches the block? The ramp. Does it push or does it pull? It's not a chain, it's not a thread, it's not a string, it's not a rope. It pushes. Whenever one thing pushes on another, there will always, always, always be a normal force. And by normal, we mean perpendicular to this surface between the pusher, the ramp, and the pushee, the block. It's got to be perpendicular to that surface. And I label it ramp on the block. Whenever one thing pushes on another, there will always be a normal force. There may also be a friction force. But if I have dry ice on slate, no friction. That's a free body diagram. I'm done. And not only that, I'm sure I'm done. I'm sure I didn't make a mistake because I followed the recipe. Now, which of those forces is causing the block to accelerate? Is it the gravitational force or the normal force? Both. It's both. It's the net or the total force. I've got to take those forces one at a time and add them. There's the plus sign right there. I take those vectors and I stack them head to tail. Once I've got all the vectors added together, the net force is just the vector sum. Okay, from the first starting place to the last ending place. Now the acceleration of the block is caused by that net force, and that means the acceleration has to be in the same direction as the net force. And we know in this case that direction is down the ramp. We've known that since the first tutorial. Okay? Now here's something very important. If I look at that table of forces, I don't see the net force on there. And that's because the net force is not a real force. It's a mathematical construct. It's the vector sum of all the real forces. I remember giving an oral exam to a grad student here for his doctoral work, and I was just having him do a free body diagram of a complicated situation. And I was playing devil's advocate, and I just said, so any other forces? And he'd find another force. Any other forces? He'd find another force. He got the free body diagram perfect. But did I let it go and say, good job? No. I said, any other forces? He looked all worried. Oh yeah, the net force. No. You never put the net force on a free body diagram. You only put the real forces due to real things that you can smell, taste, and touch. Now folks, let's go back to this pretest. Let's see if you learned anything just now. There are two vectors that describe the motion of this crate. The velocity down and the acceleration up. This free body diagram for the crate has to screen one of those vectors. This diagram has to cause one of these vectors. Which one is it? Don't say it out loud. Just tell me, is the upward force by the snow going to be greater than, equal, or less than the 50-pound weight of the crate if the crate is moving down through the snow and slowing down? Let's see if you got your money's worth today. Are you done? Be done. Good. 48 of you are on the bus. A blessing on your head. Okay? Now, here's the thing. This vector is oh so tempting because we can always see it if we've got any kind of imagination. But the success you will find on the next midterm will all be in ignoring that vector and concentrating instead on this vector. You have to ignore the velocity and recognize that this diagram has to scream that acceleration. If the acceleration is up, I gotta have more force up than down. The extra force up we call the net force. Okay? How much extra force up we have, more than we have down.